Welcome back to another video, guys. So last time we discussed the Streams API in Java and ran some tests to determine its performance characteristics. But on that last video, I got a comment from one of my subscribers. Tan Al says, "I'm happy to see people doing this kind of testing themselves. However, the testing methodology is not really the best. In order to get valid results, the test shouldn't be done only once with a cold JVM. I'd suggest looking at the Java Microbenchmark Harness, JMH, for a way of doing it properly." I'm talking about the way the JVM profiles and optimizes the code at runtime based on detected hotspots. For accurate testing, the same method needs to be called multiple times, the peaks discarded, and then the runtimes averaged to get better overview. Also, for the first example, the summation of numbers, random list content should be generated before each iteration, otherwise the runtime might notice that the results are always the same and replace entire function calls with constant values, which might skew the times by a huge amount. Of course, when my subscribers ask, I must provide. So today, we're going to be rerunning the experiments from the Java Streams API video, which, by the way, if you haven't watched, click the title card and go watch that video. I think you'll learn something pretty interesting about Java Streams API. I talk about why Java added it in Java 8, what it's useful for, and when you want to use it in your code. Today we're going to be rerunning those experiments using JMH microbenchmarking, and hopefully we'll get some more accurate results. So here's our integer sums, like benchmark runner skeleton. We're going to test, like last time, the for loop, for each loop, sequential stream, the pre-built sequential stream, manual concurrency at various partition levels, parallel streams, and then a pre-built parallel stream. Now when we're going to be designing this, we have to be careful of a few things. The first one is constant folding. So with constant folding, the JIT compiler might replace a function call to a constant, or a list of constants, with its result. So that could drastically skew the results. In order to avoid that, we're going to be using some JMH utilities like state. The other thing we have to be worried about is dead code elimination. Notice that in the skeleton, all the methods are void. They don't have any return value. We don't want the JIT compiler to be eliminating this dead code that's not being used, and so we're going to have to find a way to enforce it to actually evaluate the blocks inside of these methods. So the first thing we're going to do is decide how big we want our list of longs to be. So I think let's start with 1 million. Next, in order to avoid constant folding, let's define a inner class here. Call it range. And it's simply going to hold our list of longs. In the spirit of the streams video we made last time, I'm going to implement this using a long stream. We can do that by first taking all the numbers from 0 to the limit. Then for convenience, let's just map them to longs, to random longs using thread local random. Finally, let's box them to long objects, and we have our list of random longs. Is this a stupid way to do this? Yes. Next, we're going to use JMH here to set the scope of this static class to avoid constant folding. All right, next up, I'm going to fill in all of these empty bodies with the methods that I want to benchmark. Alright, cool, so I've filled them all in except for manual concurrency. So for manual concurrency, let's add a parameter to test against. Okay, so our parameter here is going to be the number of partitions we want, which is essentially like the number of threads we want to be running concurrently. Let's choose 2, 5, 7, and 10. Now we can pass the execution plan into our manual concurrency method. And so now when we run the Java Streams manual concurrency routine, we can pass in the partition value that's going to be set by JMH from the execution plan. There we go. Okay, the last thing we need to do is decide how we want to run these tests. So we'll run it basically a total of 5 times and discard the first 2 and collect data on the last 3. And before that, let's warm up. I think 5 should be okay, instead of the default 20. Let's use average time to be consistent with our last video. Cool, now I just have to add these annotations to each of the methods. Now finally, we have to be careful of dead code elimination. As you can see, all of these methods are just void methods, and the result of these calls could functionally just be discarded. In order to avoid that, we're going to go with the black hole solution, which essentially means we're going to pass the result of these calls into the black hole. Should force the JIT compiler not to optimize this by discarding the results of these method calls. Now we've successfully taken care of, or hopefully, constant folding and dead code elimination. And our first benchmark test is finished. Let's move on to the date parser. All right, so for this one, we're going to use the same date generator. Just going to take all the dates from 1990 to the year 3000 and put them into a list as strings. So this time, instead of just setting partitions, we're actually going to set up by randomizing the order of the dates in the dates list. The point of this is to, again, try to avoid that constant folding issue or any other JIT compiler optimizations. And so here are our 3 benchmark tests we're going to be running, one for array list, one for linked list, and one for parallel streams. And we're going to be using the execution plan that generates the dates and randomizes their order. Last thing we have to do is add the black holes in order to once again avoid dead code elimination. So I'm just going to change the name of these so that we can tell that they're for dates. So I think we're ready to run the benchmark. We can see warm-up fork 1 out of 2, so it's going to do 2 warm-ups, and then it'll run 3 tests. So after a few hours, the benchmarking finally finished. So let's take a look at the results. So before we actually look at these date ones, I want to take a look at the results I had in my previous video. As we see here, it looks like last time I found that the linked list had for some reason performed better than the array list implementation. But as we see now using proper benchmarking, the array list and the linked list are essentially the same. The linked list again performed slightly better, but insignificantly, I think. And of course, the parallel stream outperformed them quite a bit. Now let's take a look at the integer sums. So the for each loop, for loop, and all of the concurrency implementations, as well as the parallel streams, all performed very similarly. The only time we saw performance degradation looks to be in the sequential streams. These results are very similar to what we had in the previous video. These results are pretty similar to what I got in the previous video. So without using the JMH benchmarking, our results almost seem to suggest that the manual concurrency and the for loops would perform better than the parallel stream, which as we see now isn't the case actually. The parallel stream performs as good as some implementations of manual concurrency and as good as the for each loop. I wanted to test the integer sums again, so this time I changed the metric to throughput and increased the number of warm-ups to 20, also increased the total number of tests to 10 with 5 discarded, and the results are much more granular. As we can see, it looks like the implementations with manual concurrency, and specifically the choice of having 10 threads, increased throughput significantly compared to other implementations. The for each loop and the for loop were the next best performers, and then all of the streams experienced performance degradation. So given these results, it looks like the results of the last video were actually maybe a little more accurate than it seems compared to the using average time as a metric. So what this tells me is that there is a cost with a task like summing integers, which again is probably optimized for, to using streams for this type of task. But with the dates, it looks like the streams are the right choice. You can watch that video to get the thesis, but essentially there's a time and a place to use streams, and if you use them in the wrong place, then you will probably experience performance degradation like we're seeing in this particular example. So anyways, I hope you guys learned something from this video, and of course don't forget to like, comment, and subscribe. Thank you to Shaitan Al for this suggestion. Definitely a good experience to learn how to benchmark properly, and again, I'll see you guys in the next video. See ya.